Hey everybody, thanks for joining us. Welcome to our February 3rd Thursday webinar, Static Testing of Rotating Machines, hosted by Protec Equipment Resources, the electrical test equipment rental experts. Call us for all of your test equipment needs. We're excited to have people from all over the world again today, not just from the United States and Canada, but we have people from Australia, Colombia, Germany, Pakistan, Saudi, Turkey, the UK, the UAE. Thank you guys for staying up late or waking up early to join us. Thanks to our competitors who are listening at this time. You know who you are. My name is Matt Medinka, Director of Marketing and your moderator for today's webinar. If you check on your controls under the handouts section, you will find this presentation in an outline view, and you can download that if you so choose. This presentation is currently not offered for continuing education units. However, we're working on that with NETA and PE certifications. If you attended our January webinar, that session has just been approved for IEEE credit, and we will follow up with you next week on how to submit for that credit. If you have any questions throughout the presentation, please send them through the questions tab. We'll address as many questions as possible at the end of the webinar. We have noted the questions from your registrations, and we'll go through as many of those as we have time for. You will remain muted throughout this event, even in the Q&A, so please use the question function and we'll try to answer. Please don't hold your hand up. We have too many people on the webinar. Please use the question function. We may not get to all your questions, so if you'd like to contact us after the event, you can send your questions to marketing@protecequip.com, and we'll make sure to get those answered for you. This webinar is free to watch. Please follow all industry and company policies and safety procedures when performing live tests. Now, I'd like to introduce you to your presenter today. Many of you know him already. You might have met him last month. His name is Tom Sandri. He's a 30-year industry veteran, starting off with an electrical manufacturing company that is now known as Megger. Tom worked for Protec for several years and then Shermco for the last 9 years. Tom is back with us at Protec, and we're happy to build additional learning tools and content for you guys to be able to increase your knowledge and perform your jobs more effectively. So without further ado, Tom, you have control of the board.
Hello, I am Tom Sandri, and welcome to this month's Third Thursday webinar. Hey, this webinar is going to cover static testing for rotating machines. The topics that we're going to include: the electrical motor insulating system. What insulation do we actually test? What is the point of testing motors? Motor failures and reasons for motor insulation failures. All right, to understand where and what the insulation systems are in an electric motor, let's step through the process of rewinding a motor. That way you can see where the insulating systems come into play. There are basically two insulation systems in any motor: the ground wall insulation and the turn-to-turn insulation. So, step one. The electric motor stator is without insulation or wiring. In step two, paper insulators are installed into each of the slots. This is called the ground wall insulation. The primary function of insulation is to separate the conductor from the stator core to allow a voltage difference to exist between the two. The most common taping material used to provide this electrical separation are glass, mica paper, and mica flakes. All of these have excellent electrical insulating properties. However, they have terrible mechanical properties. Glass and mica tend to shatter when exposed to the severe vibrations presented in a generator. To diminish the mechanical stress on the insulation, winding designers have chosen to impregnate the tapes with an organic compound. The organic compounds frequently used are asphalt, polyester, and epoxy. Which compound exists within the motor or generator is dependent on which company manufactured the windings and the year of manufacture. In step 3, Coils of wire, random wound, or form coils are installed into the slots. Winding designers have gone to great lengths to make sure they put in as much copper and as little insulation as possible in each coil or bar. What construction they choose depends on the size, at maximum generating efficiency, of the machine that you want it and the amount of money that you want it to spend. Medium to high voltage, greater than 2300 volts, are made with form wound coils, while lower voltage machines tend to be random wound. Form wound coils are designed such that the turn voltage stress is constant. These are different from random wound motors, where the turn voltage stress will vary considerably and can be the maximum phase to ground voltage. There are three widely used designs of form wound stator windings: a bar or half coil, a multi-turn coil diamond winding, or a multi-turn coil concentric winding. Now, step 4, dip and bake. The final step is called dip and bake, and it is exactly what it sounds like. A finished winding is submerged in a vat of special resin. Following the resin soaking process, the stator or armature is placed in a baking oven to cure. This is designed to hold the windings in place, and often up to 3 cycles may be performed. Now, what is the point of testing motors? Well, some industries have motors that are critical to the operation of the facility, like a power plant. If a critical motor shuts down, it can shut down the whole plant. That can cost the company hundreds of thousands of dollars per day or even by the hour. Without predictive maintenance, you can have motors that suddenly blow out and shut down, even to the point where there is a catastrophic failure and the motor is destroyed. So let's talk about some of these motor failures. First, let's look at winding blowout. Winding blowouts can be caused by overheating, overloading, that causes insulation to degrade and then fail. Also, phase to ground fault. Phase to ground faults can also be caused by overheating, overloading, that causes insulation to degrade and then fail. Bad bearings could have come into play here as well. As you can see in this example, the rotor grounded against the laminations. Now, other reasons might be temperature. Small temperature increase causes large decreases in insulation resistance. Or the failure could have been mechanical stresses, vibration, thermal expansion and contraction, magnetic forces, bearing problems, etc. Or the failure might have been winding surface contamination, dirt or moisture, oil, etc., mixed with particles. It lowers insulation resistance and can reduce ability to dissipate heat. Also, insulation breakdown due to voltage spikes from starting and stopping the motor and poorly tuned variable frequency drive power supplies. Other failures could be partial discharge, electrical discharges within void inside the insulation that create heat and can lead to hot spots. Or the failure could have been chemical fumes. These attack the insulation directly. Possibly shorted turns. These form closed loops. Current induced in loops dissipate as heat and breaks down the insulation further. The result, destroyed ground insulation. Let's take a deeper look here at temperature. A small temperature increase lowers the insulation's ability to contain current, which increases heat in the motor. Overloading the motor for extended periods and running it above the design temperature reduces the insulation life, thereby reducing the motor life. For every 10-degree rise in Celsius over the normal operating temperature of the motor, it reduces the insulation life by half. All right, let's look deeper at mechanical stresses. Vibration causes insulation wear. But also among the mechanical stresses, thermal expansion and contraction inside the motor causes insulation wear. Also, bearing problems can cause mechanical damage to the rotor and windings. Also among mechanical stresses, magnetic forces inside the motor cause physical movement in the windings, in turn leading to insulation damage and degradation. All right, let's move on to other insulation failures, such as winding surface contamination, dirt or moisture, oil, etc., mixed with particles. Windings coated in dirt will cause heat buildup. Wind blowing abrasive dust through a motor, for example at a cement plant, can lead to surface contamination. In salt mines, we might have salt crystals. Grease used to lubricate bearings can drip on the windings. Motors exposed to water at a food processing plant can lead to surface contamination. Well, the results: lower insulation resistance and can reduce the ability to dissipate heat. Causes insulation to weaken, high heat and current. Completely worn insulation can cause turn-to-turn or ground faults. All right, let's look at insulation breakdown. Breakdown can occur due to voltage spikes from starting and stopping the motor. Spikes are 3 to 5 times normal operating voltage. The spikes are fast, short-duration electrical transients in voltage. Now, this could be because of poorly tuned variable frequency drive power supplies. Also, starting and stopping a motor too frequently. When starting a motor, there is a high inrush current, 6 to 10 times normal operating current. Now let's focus on those chemical fumes. They form by products from various manufacturing processes, or from ozone from partial discharge. All attack the insulation directly and erode the insulation. Now, the net result of all the factors degrading the insulation: they form closed-loop shorts in the turn-to-turn windings. The current induced in these loops create high heat and breaks down the insulation further. The result is a turn-to-turn short, which becomes a short through the ground wall insulation. All right, now let's move on to the static motor testing techniques. The topics here that we're going to cover: how do the techniques work, failures they can find, and failures that they cannot find, and failure limits. So, winding resistance, inductance, and impedance. These type of tests find winding balance and motor connection problems. Insulation resistance. This test identifies motor contamination. Polarization index or dielectric absorption. These tests assess strength of ground wall insulation. The step voltage or high potential tests. These detect ground wall insulation and cabling issues. And also the surge test. This is used to find winding insulation weaknesses. Let's start with that winding resistance test. Winding resistance can be measured from phase to phase with balance calculation, which is most common, or by coil if there is access. Winding resistance measurements detect problems in motors which other tests may not find. These problems include partially or fully shorted coils, poor crimps or connections, imbalance between phases, improper turns on phases, and incorrect coil phasing connections. Now, studies conducted by IEEE and the Electrical Power Research Institute, EPRI, on electrical rotating machinery failures show that 48% of motor failures are due to electrical failures. A motor or generator is broken down into two main components, insulation and mechanical. The mechanical condition and structure of the rotor or stator affects the winding resistance. Winding resistance tests apply a known DC current through the windings, measure the resulting voltage drop across the windings, and calculate the resistance. One should not apply more than 10% of the winding current rating, as this will warm the winding and create a changing resistance value as the copper or aluminum heats up. Safety is an important consideration when testing winding resistance. Motor or generator windings can store a large amount of energy when DC current is injected into them during the test. This is known as inductive charging. This energy must be dissipated safely from the windings after the test current is stopped. Winding resistance test readings can check against factory stated values. Now, a common diagnostic technique is to compare with previous readings. Since winding resistance is affected by temperature, it is important to use temperature correction factors when applicable. Winding resistance tests are compared between the three phases on a three-phase motor. Several standards provide maximum deviation percentages, but typical limits are 1 to 3% between the mean average for the three windings. Excessive differences in resistance readings between phases may indicate a possible problem inside the motor. Winding resistance is also used for measuring I²R or heat losses in the windings. All right, winding resistance tests. What failure modes can be found? Well, winding resistance balance with pass-fail 2 to 3%. Resistive connections internally or externally. All strands are not connected with several in hand. Hard shorts in the windings to other turns, coils, and ground. Incorrect coil or group connections. Partial blowout of multi-strand random wound coils. Or wrong gauge wire in a coil or feeder cable. Possibly wrong turn count. Alright, next let's move on to the insulation resistance test. Insulation resistance test, also known as megohm test. An insulation resistance test elevates the voltage in the windings and measures how much current exists between the windings and the frame or ground. Then calculates the insulation resistance. Now, generally the test voltage is close to the operating voltage of the motor. For an example, a 480 volt motor would be tested around 500 volts. Insulation resistance is among the most common motor tests. In an insulation resistance or megohm test, the voltage applied and the total leakage current are measured between the windings and the motor frame or ground. Ohm's law is applied to calculate the resistance in megohms. Basically, resistance equals the voltage divided by the current. A temperature correction factor is applied to correct the megome measurement at present temperature to what it would be at a standard temperature. Now, according to IEEE 43 and ANSI ESA standards, the standard temperature is 40 degrees C. The leakage current of a used motor is often surface current running in the dirt on the outside of the windings. The dirt contains particles of dust, oil, grease, moisture, etc. Conduction current that flows through weak ground insulation to ground is often dwarfed by the surface currents. Therefore, the insulation resistance or megome measurement is sometimes referred to as the dirt test. Megomes tend to drop with increasing amounts of dirt. A megome measurement on new motors is often not interesting, other than to check that there are no direct shorts to ground. Users will often go directly to a high potential or high pot test, which we're going to discuss later. Hey, but before we move on any further, let's talk about the currents that are involved in an insulation test. Insulation resistance-based tests are among the most common motor tests, and these tests deal with more types of current than many technicians realize. The currents involved in an insulation resistance test are the capacitive current. A capacitive inrush current brings the potential in the motor up to the test voltage by charging it. This current drops quickly and reaches zero within a few seconds after the test voltage is reached. For large motors with high capacitance, the inrush current is high. Total leakage current failure limits must be set high enough to avoid tripping the limit during this initial phase of the test. We also have a thing called absorption current. Absorption current polarizes the insulation. This current also goes to zero or very near zero within 30 seconds to 1 minute in random wound motors. Form wound motors take much longer due to the layers of insulation used between turns. The change in absorption current over time is what is used to calculate polarization index and dielectric absorption ratios in an insulation resistance test. The PI and DAR will be discussed more a little bit later in this training. We also have a thing called conductance or conductive current. Conductance current flows between the copper conductors and ground through the bulk of the insulation. Now, this current is usually zero if the motor is new or is undamaged. As the motor insulation ages and cracks or is damaged, conductance current may flow depending on the test voltage that is applied. Conductance current tends to accelerate with increasing voltage. This current is sometimes referred to as leakage current or as part of the leakage current. But now let's focus on surface leakage. According to IEEE 43, surface leakage is the current flowing in the dirt on the surface of the windings to ground. It is called surface conduction current in other standards. A dirtier motor has higher leakage current and a lower megome result. There may be an increase in the surface leakage current on motors with a stress control coating on the end windings. Now, after 1 minute with a random wound motor or 5 to 10 minutes with a form wound motor, the surface leakage current is typically the only current remaining unless the insulation is weak or damaged. And that brings us to the total current. The total current is the sum of the four currents. A motor and insulation tester measures total current. the total current equals or is very close to the surface leakage current at the end of the insulation resistance test. This gives the operator a good measure of how dirty or contaminated the motor. It also alerts the operator to a possible catastrophic connection from the windings to ground. Next, let's take a look at standards and temperature compensation. ANSI AR100-2015 and IEEE 43-2013 make the same recommendations as follows. It is recommended that motors with low insulation resistance test readings not be subjected to high voltage testing. The tables shown provide recommended test voltages and minimum insulation resistance values at the standard temperature of 40 degrees Celsius. The limits shown in the table are for windings at a temperature of 40 degrees C. The megohm test results are temperature compensated because the windings usually are not at this temperature when tested. Some insulation testers will do this automatically if the winding temperature is entered into the tester. Resistance values must be temperature compensated when insulation resistance is tracked over time. The temperature must also be above the dew point for accurate comparisons of results. The most common temperature compensating formula states that the insulation resistance drops by a factor of 50% for every 10 degrees C increase in temperature. Therefore, the insulation properties drop precipitously as the temperature rises. Insulation resistance of 10,000 megohms, 10 gigohms, at 20 degrees C, which is about 68 degrees Fahrenheit, drops to 2,500 megohms at 40 degrees C and to 39 megohms at 100 degrees C. Now, there are several other temperature compensation formulas. The prior example is likely the most conservative. Different types of insulation systems in form wound motors have unique temperature characteristics. Now, these are only obtained from the manufacturer of the motor. The bottom line is temperature has a significant effect on insulation resistance, and it must be compensated in order to get the best test results. So, an insulation resistance test will determine if the motor has shorts to ground, measure current leakage in a dirty motor and surface leakage caused by dirt, water, and other contaminants. It helps determine if ground wall insulation is good. And trending the insulation resistance can tell you when to schedule reconditioning or cleaning. Now, failures that are not found with an insulation resistance test would include weak insulation at elevated voltages, any turn-to-turn failures or weaknesses. Now, these failures require surge tests, which we're going to discuss later. Connection problems, open phase, phase-to-phase fault. All right, let's look at polarization index tests. Polarization index and dielectric absorption tests. Now, a valuable property of insulation, but one that must be understood, is that it charges during a test. The polar DC field that's applied by the tester causes realignment of the insulating material on the molecular level as dipoles orient themselves with the field. This movement of charge constitutes, of course, a current. Its value as a diagnostic indicator is based on two opposing factors. The current dies away as the structure reaches its final orientation, while leakage, promoted by deterioration, passes a comparatively large constant current. Now, the net result is that with good insulation, leakage current is relatively small and resistance rises dramatically as charging goes to completion. This changing resistance is exactly what an experienced technician wants to see. Deteriorated insulation will pass relatively large amounts of leakage current at a constant rate for the applied voltage. This will flood out the charging effect. Polarization index, or PI, is a ratio of the megohms after 10 minutes divided by the megohms after 1 minute. This test is primarily conducted on form-wound motors and generators. An instrument records megohm data after the 10 minutes, and the resulting graph and PI ratio can provide additional information about the winding insulation beyond the megohm number itself. The PI test, like any resistance measurement, is the measurement of voltage and currents. PI is the ratio of leakage currents assuming constant voltage. PI equals R sub 10 divided by R sub 1, where R sub 10 and R sub 1 is the resistance in megohms at 10 minutes and 1 minute, respectively. Resistance equals voltage divided by current, so the PI formula reduces to the PI equals I sub 1 divided by I sub 10, the current at 1 minute divided by the current at 10 minutes. Because the changes in current may be very small, the IEEE 43 2013 states, when the insulation resistance reading obtained after the voltage has been applied for 1 minute is higher than 5,000 megohms based on the magnitude of applied direct voltage, the total measured current can be in the sub-microamp range. At this level of required test instrument sensitivity, small changes in the supply voltage, ambient humidity, test connections, and other non-related components can greatly affect the total current measured during the 1 minute to 10 minute interval required for a PI test. Because of these phenomena, when the insulation resistance is higher than 5,000 megohms, the polarization index may or may not be an indication of the insulation condition and is therefore not recommended as an assessment tool. In summary, for motors with no or little absorption current, where the total leakage current stabilizes within 1 minute, polarization index values are close to or equal to 1. In this case, PI is not a proper evaluation tool. This is often the case for random wound rotating equipment. The table seen here shows minimum IEEE 43 2013 PI ratings. Alright, now let's move on to DC high potential or high pot tests. A DC high potential, or simply high pot test, is essentially an insulation resistance test like the megohm and polarization index test that we discussed earlier. The main difference is that the high pot test is performed at a higher voltage. The test elevates the voltage in the windings and measures how much leakage current exists between the windings and the frame, ground. The insulation resistance is then calculated. As a rule of thumb, the test voltage can be 2 times the operating voltage plus 1,000 volts. For example, a motor with an operating voltage of 480 volts would be tested around 1,960 volts. Alright, so let's review how a DC high voltage potential test works. DC voltage is applied to open, disconnected windings by the high pot tester or motor analyzer. The DC voltage potential in the windings is rapidly raised to a predetermined level, or raised in steps up to this level, depending upon what test method is going to be used. As the voltage is raised, several currents, as discussed earlier, will flow into and possibly out of the windings to ground. The combined total of these currents are measured by the high-pot tester. And here we see a demonstration of the step version of the high-pot test. At the last voltage level, we then look at the high potential reading. All right, let's once again though review those currents. Capacitive current or geometric capacitive current. This is also called the inrush current. The windings have capacitance. Current is required to elevate its voltage potential. This current typically drops to zero within seconds after the test voltage provided by the motor tester is stable. And we also have that absorption current. This current is present during the atomic and molecular polarization of the insulation and is the current one is interested in during the PI test. This current will drop to zero or near zero over a period of time that varies by motor. It can happen in seconds or may take 10 minutes or more. We also have that volume conduction current. This is the current that flows through the entire volume of the insulation between ground and the conductors. Now again, in good windings, this current is usually zero or near zero and depends on the composition and condition of the insulation system. People sometimes think of this current as the leakage current. It certainly leaks through the insulation, but the next current is usually the main leakage in the used motor. And that is the surface conduction current. This is often referred to as surface leakage current. The surface conduction current runs over the end winding surfaces of the insulation. It is a result of surface contamination, dirt, and moisture on the windings that are connected to ground. As the contamination level increases, the resistance of the contamination drops and the current increases. As the voltage increases, the current increases more or less proportionally with the voltage applied by the motor tester. For used good motors, this current will dwarf the absorption and volume conduction currents because of relatively lower resistance in the surface contamination. For new, totally clean and dry motors, this current should be zero or near zero. The motor tester measures the sum of all the above currents in microamperes and displays it along with the test voltage. To add to the list of what leakage current may mean to people, the total current measured by insulation resistance and high potential testers is also often called simply leakage current. IEEE 95 calls this the measured current. Now let's look at definitions. Definitions from IEEE 95 recommended practice for insulation testing of AC electric machinery, 2300 volts and above, with a high direct voltage. The first definition we see is breakdown current. The current discharged as a result of insulation failure. The peak value of this current may be very high, reflecting the energy stored in the capacitance of the windings. Normally, this current cannot be accurately measured. We also have breakdown voltage. This is the voltage at which a disruptive discharge takes place through the volume or over the surface of the insulation. And we have high direct voltage, also referred to as overvoltage. A unidirectional voltage whose magnitude is greater than the peak value of the normal RMS line to ground rating of the insulation system under test. All right, let's look at insulation failures. Electrical insulation failure or breakdown is usually indicated by an arc, a sharp capacitive discharge at the failure location. There are times when failure or partial failure is indicated by a large abnormal change in the measured current or by erratic behavior of the measured current. Warnings of insulation breakdown by accelerating measured current can start within as little as 5% of the breakdown voltage. However, it can also start much earlier. Let's look at those auxiliary equipment during a test. Before starting an overvoltage test like a DC high potential test, the following components should be shorted to ground. Stator resistance temperature detectors or thermocouples. Other devices associated with the stator windings. Current transformer secondary windings. Rotor windings, both terminals and the shaft. Objects close enough to become charged. Motor tester chassis. Surge arresters and surge capacitors. Now, these must be disconnected prior to any overvoltage test. Surge arresters have resistive elements, and surge capacitors have discharge resistors. They are in parallel with the winding under test and will invalidate the current measurements. Now, for single-phase motors, start and run capacitors should also be disconnected. Let's take a look at the high potential test known as the DC ramp test. The ramp test is performed with a slowly rising voltage. The final voltage is the high pot test voltage. The voltage and measured current is recorded every second or few seconds during the ramp test. The initial increase in the current is mainly due to capacitive inrush current. This current quickly stabilizes and remains constant throughout the test if the voltage increase, the delta V divided by delta T, is constant. The capacitive current will equal the winding capacitance times the change in voltage divided by the change in time. Now, there may be some absorption current throughout the ramp test. The increase in the current as the test proceeds is due to surface leakage current. If the insulation is weak or breaking down, there will also be an accelerating volume conduction current through the insulation. For a good motor, the slope of the curve is fixed. For example, the curve is close to a straight line, since a higher voltage typically produces a proportionally higher measured current. The amount of surface leakage current indicates the amount of contamination and or moisture in the windings. An acceleration in the total measured current after the initial current inrush has settled indicates a breakdown of the insulation. At the end of the ramp voltage, the voltage is held steady for a short while. The capacitive inrush rapidly drops to zero, and the remaining measured current is mainly due to surface currents and conduction leakage currents if the winding insulation is breaking down. The next high potential test we're going to look at is the DC step voltage test. The high pot step voltage test is recommended for motors with an operating RMS voltage of 2300 volts and higher. It is done on any motors with any operating voltage when more information than a 1-minute high pot test provides is needed. In a high pot step voltage test, The voltage is usually raised in equal steps. At each step, the voltage and measured current are recorded after 1 minute per IEEE 95. The number of steps is determined by the test operator and can be anything from 5 to 30 or more voltage steps. 10 voltage steps are common for medium voltage motors. More steps may be used for high voltage motors. High-pot step voltage tests provide much more information than a 1-minute high-pot test because the data is recorded as the voltage is raised. By charting a current versus voltage curve, one can usually tell if the leakage current is mainly due to contaminated dirty windings or due to a breakdown of the insulation. So let's take a look at some test results. Here we have a good result. A 3,300 volt motor was tested with 7,600 volts. Good windings will have a curve that is more or less a straight line, as shown in this graph. The current depends on how contaminated the windings are. In this case, the current and contamination level is low with a total leakage current less than 1.4 microamps. Now here's a test result for an okay result. Here a 4,000 volt motor was tested using a voltage of 9,000 volts. 4 10-point step voltage tests were done over time. The two bottom curves from the first two tests are very good. The red and blue curves from the next two tests show minor acceleration in the current. But the maximum current is still relatively low at 11 microamps, and the acceleration starts above 7,000 volts, significantly above peak operating voltage. The elevated total voltage is mainly due to increasing winding surface contamination, including moisture, judging from the previous tests. If the acceleration in the current was significant and the blue line moved more towards vertical, it would indicate a breakdown of the insulation. Now these test result here shows concern. Here a 6,000 volt motor was tested at 11,700 volts. The test represented by the blue curve did not shut the test set down early because the maximum current at about 25 microamps did not reach the total leakage current limit, and the acceleration of the current was not high enough to exceed the chosen trip level of 2, the current rate of change between voltage steps. However, the accelerating leakage current and the current level at the end of the test indicates weak insulation that is starting to break down. The current acceleration starts slowly at about 6,000 volts, so the motor condition is concerning, but still okay. No arc was detected during the test, since that would have shut off the test early. With a lower trip limit, the test would have shut off before reaching full test voltage. Now, this test shows a problem. A 4,160 volt motor being tested at 9,320 volts. In this test, there is a sudden breakdown of the insulation between about 5.6 and 6.5 kV, and the test is shut down at the end of step 7 at about 6,500 volts because the acceleration in the measured current exceeded the trip limit from step 6 to step 7. With rapid acceleration of the current, the chance of an arc increases significantly, but that did not occur here. the breakdown is happening around the peak operating voltage of 5,882 volts. With this result, the motor may be able to operate for a while, but it is on its way to a complete breakdown. In general, any deviation from a smooth curve should be viewed as a potential warning. A very abrupt drop in conduction current is rarely found, but when it occurs above the peak operating voltage for the winding, it may indicate approaching insulation failure. Mechanical abrasion and cracking may cause abrupt and unexpected insulation breakdown. All right, let's talk about when to perform a high potential test. Well, we can test as long as the insulation resistance exceeds megohm requirements. And always test new, rewound, and reconditioned motors. Get yourself a baseline. In the motor shop, after the coils are installed in a stator. Also in a motor shop, during diagnosis of a motor. During regular maintenance outages. And what are the failure modes that we can find with a high pot? Early warnings of weak ground wall insulation. Dielectric strength to ground. The dielectric strength of the phase-to-phase insulation. When the megohms measured in an insulation resistance are lower than expected, a DC high pot step voltage test can indicate if the motor or device under test is dirty and or moist, or if insulation is breaking down. Since insulation resistance tests usually are done at 1 voltage and do not provide this information, a step voltage test can be very valuable. Okay, other failure modes. The IEEE standard for AC electric machinery, 2300 volts and above, states that the following insulation problems may be detected by a controlled direct voltage test. Surface contamination, cracks and fissures, delamination, moisture absorption, uncured resin, voids. And let's move away now from high potential testing and let's look at the surge test. Surge tests are important because they are the only tests that find turn-to-turn insulation weaknesses. These weaknesses start at voltages above the operating voltage of the motor and are precursors to serious failures and shutdown of a motor. Surge tests are also used to find hard shorts and several other mistakes in windings and coils. Most winding failures, including shorts to ground, start with weak turn-to-turn insulation. Once the weakness causes turn-to-turn arcs, an electrical closed loop is created. Due to the transformer action, current starts flowing in the loop. This current is dissipated as heat and creates a hot spot. More turns short out due to hot spot and subsequently more heat is created. Eventually the winding shorts to ground. Now, surge tests are also known as surge comparison tests because the results from a coil or phase is compared to the results from another coil or phase. Coils are designed to be identical, so the surge test results should also be nearly identical. When windings or phases are not identical or there is nothing to compare to, operators use the pulse-to-pulse surge test. But let's look at how a surge tester works. During a surge test, a surge capacitor connected in parallel to the winding to be tested is discharged suddenly. A sinusoidal damped oscillation is created in the oscillating circuit created between the testing device and the windings. And this oscillation has certain characteristics. A test lead switching matrix in the surge tester connects the output leads to provide a complete electrical circuit. For a three-phase stator, this is usually between two phases. One phase is energized, the other phase or other two phases are grounded. The result of the test is displayed on the screen. Next, one of the other phases is energized, and finally, the third phase is energized, which results in 3 unique waves or signatures on the surge test screen. Each step in the sequence can be done manually, one at a time, or by the push of a button activating an auto matrix. Now, the 3 surge waves are compared, and a percent wave difference, percent WD, which is also referred to as percent EAR or percent error area ratio, is calculated for each wave pair by the surge tester. The WD or EAR is calculated somewhat differently by different surge tester brands, but the results are similar. The general approach is to calculate the difference between many points along a wave pair, points on 2 waves with the same x-axis position. Add up all the differences and divide by an average. If the percent WD is too high, the surge test failed. So what causes differences in the surge test waves? Well, stator windings have impedance. This impedance is made up of the inductance L in the windings, resistance R in the winding insulation and in the windings, and capacitance C between each winding and between the windings and the core. Using a 3-phase application as an example, the 3 waves in the surge test should be close to identical if the 3 phases are designed to have the same impedance. However, not all machines are designed and manufactured with perfect balance between the phases. In 3-phase machines designed with symmetric impedance, the wave frequency and zero crossing will be different in the phases affected by a hard short, or if arcing is occurring due to weak insulation. The amplitude of the wave may also change. The formula for the surge wave frequency is the frequency equals 1 divided by 2 pi times the square root of 1 divided by LC minus R squared divided by 4L squared. Now, R2 divided by 4L squared is compared to 1 over LC. So the equation reduces to the frequency equals 1 divided by 2 pi times square root of LC. Let's look at inductance. The inductance will go down when there is a turn-to-turn short in the windings. Inductance is proportional to the square of the number of turns in the winding. As inductance goes down, the frequency goes up. An increase in frequency shifts the wave's zero crossing to the left on the surge test screen. Likewise, if there are other problems in the windings that can be found with a surge test, the inductance will change. Connection problems, for example, may add or subtract inductance to the circuit. Or they may cause the electric field generated in the coils during the surge test to oppose each other, effectively reducing the overall inductance. When the insulation is weak, a change in inductance will only show up at elevated voltages. Consequently, it will not be detected in low voltage tests and measurements. The surge test reduces false negative results, which is why the surge test is a very valuable test. If the surge test is done above the peak voltage the motor operates at, early warning of problems to come can be detected. The motor may still run fine for a while if the weakness shows up at a voltage above the peak sinusoidal operating voltage. Now, let's look at capacitance. The capacitance does not change much with most turn-to-turn shorts. However, it can contribute to the change with more massive faults. Let's look at resistance. Note that resistance is not part of this formula, which is why surge tests do not detect differences in resistance or resistive connections. Therefore, accurate winding resistance measurements are important to do in combination with surge tests, as well as in combination with megohm and high-pot tests, which also do not detect winding resistance differences. Analysis tools other than the %WD, waveform difference, or EAR, error area ratio, exist. These all are mathematical tools. The %WD or EAR is the most common and best tool, along with the good old visual inspection, which should always be done when practical. However, the rotor may cause the inductance in the stator phases to be different because of the transformer action between the stator and rotor. To address these situations, the pulse-to-pulse surge test was designed. Pulse-to-pulse surge tests when windings are different. Motor windings and coils are not always physically identical. An example is concentric wound coils, where the size of the coils are different. Another example is when coils are connected such that the stator is not symmetrical from an inductance point of view. Assembled motors with the rotor installed may have stators that are lap wound and electrically symmetrical. So, summary of what the P2P surge test is used for. It is used for concentric wound stators with a %WD or %EAR above expectations. Assembled motors, the rotor installed, with rotor influence on the stator inductance that creates different surge test waves in the three phases. For single-phase motors, any test where there is nothing to compare the standard surge test to, and any time the surge test results are questionable or in the gray zone, or to find inception voltage in partial discharge measurements. Now, how the P2P surge test works. Instead of rapidly going to the surge test design voltage and recording the surge wave after the voltage is achieved, the P2P surge test raises the surge voltage in small steps up to the design test voltage. At each step, a surge wave is recorded, and the difference between this wave and the wave from the previous step is calculated. This means that the winding under test is compared to itself as the surge test voltage is raised. Since the comparison is to itself, it does not matter that the phases are different or that there is a rotor influence in an assembled motor. Hence, for an assembled motor, the rotor does not have to be turned during the test. When the pulse-to-pulse surge test is completed, the P2P %WD or %EAR numbers for all the voltage steps are stored, and the highest P2P %WD or %EAR are displayed. If there is an arc or flashover at some voltage step, the P2P %WD will be significant for that step because the wave frequency is different from the previous step. Since the P2P surge test is looking for a change during the voltage ramp, it may not see hard shorts in the windings if the insulation around the hard or welded short is stable and strong. In such cases, there is no change or arc during the voltage ramp. Accurate micro-ohm winding resistance measurements or inductance measurements may be used to find such faults. The other alternative for assembled three-phase motors is to turn the rotor between each surge test so that all three waves line up. If they cannot be made to line up properly, there is a failure. Turning the rotor may not always be possible or practical, making the P2P surge test a very valuable tool. The pulse-to-pulse surge test should be used in combination with accurate winding resistance measurements anytime it is uncertain if the standard surge test is a pass or a fail. Which brings us to the surge test pass-fail criteria. Lead-to-lead, phase-to-phase surge comparison tests. The general guideline for a good or pass result is that the lead-to-lead percent WD or percent EAR should be less than 10%. However, there is a gray area around 10% for lap wound motors. Concentric wound stators may have differences up to 20%, sometimes even more. Many assembled motors, especially fast-running small motors, may have big differences because of influences by the rotor. Pulse-to-pulse or P2P surge tests. This is a test done on one coil or one phase of a motor at a time. The surge voltage is automatically raised in small voltage steps, and the surge wave at each voltage step is compared to the wave from the previous step. This means that the coil phase is compared to itself. The percent WD or percent EAR is calculated at each step. The maximum percent WD or percent EAR seen by the tester is displayed on the screen. A bar graph of all the WD percentages for each voltage step can be displayed on the tester and be included in test reports. When there is an arc turn to turn in a winding, the bar graph will usually have 1 to 3 tall bars above 30% at the point where the arcing started and above. So, pulse-to-pulse percent between 15% and 30%. Pass-fail interpretation in two common cases of elevated levels of P2P. If there are a few bars at the beginning of the graph, the left side, low voltage, up to 30%, the result is a pass. If there are many bars at the right side of the graph, the high voltages, that are up to 30%, partial discharges may have been detected. Flashover in weak insulation, arcs, is typically represented by 1 to 3 bars above 30%. Note, the P2P test is not designed to be a partial discharge measurement and does not accurately detect when partial discharge starts. But with enough PD, several higher bars will usually be present in the P2P bar graph. The presence of partial discharge does not necessarily mean there's a failure or problem, but can mean that the insulation is starting to weaken, especially in low voltage motors. Now, around 30% and above, the partial discharge typically turns into an arc. Now, although lead-to-lead WD percent less than 10% is normally used as pass, The 8% is a more conservative limit that is better for motors with a high turn count. And that concludes our webinar on static testing of rotating machines. Now, we will address as many of the questions as possible, and we will get back to you if we are unable to address your question during the remaining minutes of this webinar. I'd like to thank you for your attendance and taking the time out of your day. I hope you have found value in this webinar, and we look forward to seeing you in the next Third Thursday webinar offered by Protec Equipment. Thank you.
Hey, thanks, Tom. Great stuff. I know this one ran a little bit longer than last one because there's so much good stuff to talk about. Before we get into the Q&A, if you have any questions, put them in the question little drop-down tab there, and you'll be able to ask your question, and we'll get to answer it. We got quite a few questions that were asked beforehand. Before that, though, if you're going to be at NEDA coming up, that's in about 10 days. We're going to be in booth 215 in the trade show area. We're going to have a huge booth this year, lots of fun. We're going to have this big video screen. Tom and I are going to be doing a podcast. We're going to live cast that on YouTube and LinkedIn. So come by and listen to us. We're also going to have a big punching bag game. So come represent your company, win some prizes there. So join us for NEDA Power Test in Denver beginning the week of February 28th. Tom mentioned our next webinar is going to be March 17th. That's the medium voltage cable test and diagnostics part 2. A lot of you already signed up for that. I'm going to go in the chat right now and put a bunch of links in here. So you guys, if you want to register for any of these, I have the March, April, May webinar links in there. If you just want to go to our website and see the webinars listing, click on that. If you missed the January webinar, you can watch the replay. I put the link in on that as well. So let's get to questions. So Tom, first question is from Michael Sykes from Excel Power. He says, which is better for analysis of greater than 13 kV machines, partial discharge, power factor, or SFRA trending?
It's a very, very interesting question because it's sort of like going to a medical examiner and saying, which is the best overall test for determining the health of a person? Should we focus on, throat and ears? Should we focus on, I'm not a doctor, I just, play one on TV, but name your particular medical examination. And it's sort of what we have here in this question, when we really look at what is partial discharge looking at, what is power factor looking at, and what is FRA trending looking at. They all obviously are diagnostic-based tests, but partial discharge particularly is looking for voids that are developing and growing within the bulk of the insulation. It could be a very, very useful diagnostic test because normally in a lot of stators, there is going to naturally be partial discharge in there, and that your motor can be running flawlessly for the next 30 years under this condition. So really what we're looking at with partial discharge is a trending. We're looking at how fast the partial discharges are growing to determine if they are just status quo or if they are reaching dangerous levels. We also analyze the partial discharge patterns. Through analyzing the patterns, we can determine if the partial discharges are at the inner core of the windings, for instance, from the conductor into the insulation, if it is in the bulk of the insulation, or if it is out at the end winding. So we can also use the PD patterns as symptoms to help us lead to what the root cause failure mechanisms may be. For instance, delamination at the conductor to insulation might be where we have a lot of cycling of the motor starting and stopping. Temperature coefficients are different between the copper and the insulation, so we have a delamination or shearing that would show us up in the pattern where the PD is starting at the conductor. So again, we're looking at something that can maybe give us indications of things that are affecting our insulation. Again, partial discharges could be caused by loose wedges, which during operation, the running and the vibration starts to cut and erode the end winding insulation. We get PD starting out at the end windings. So a very useful test. It could look at the motor. Again, online PD is ideal because now you're looking at the thermodynamics of the motor, the vibration of the motor, and you're looking at how it's affecting or how different mechanisms are affecting the insulation. Now, power factor, phenomenal test. Really excellent for tracking and monitoring the dielectric losses in the insulation. Again, it really is useful if we have a baseline to start with, but much like a lot of the insulation tests where we call them the dirt tests and so forth, as contaminations get into the insulation, the dielectric losses are going to increase. And with power factor testing, we're using alternating current. We're really looking at the capacitance of the specimen under test, and we're looking at the changes in the dielectric losses over time. Again, these changes in the dielectric losses are typically attributed to deterioration, contamination, and possible breakdowns taking place. So again, we're really focusing heavily on the insulation here. SFRA is a very fascinating one because really what SFRA is looking at is it's injecting signal in, signal out over a band of frequencies. And when we really look at the mechanical structure of a device, it is made up of inductance, capacitance, and resistance. Now, over time, through vibration and so forth, if things are coming loose or jolting within the motor, it could change, for instance, distances between windings, which would affect capacitance. Loose connections or so forth could add resistance or change inductance. So the SFRA pattern is actually very fascinating, where it's an electrical test that quickly tells us if there are mechanical changes occurring within the motor. But as you can see by my very bloviated, long-winded answer, I really can't say which is the best. It really is what are you most concerned, or where do you want to focus on. If I had to select two, I like the SFRA trending. However, I do have to take the motor out of service to do this, but it's a quick test to tell me if there's been anything mechanical that has changed inside the motor. The partial discharge can be done as an online test. So I really like this one because it lends itself to predictive maintenance, and partial discharges occurring and trending them over time could give me clues as to different failure mechanisms that are causing the PD. But that's about as deep as I can get into it without going for the next 45 minutes to an hour. Michael, if you want, contact me privately and we can really go deep into this conversation.
Great, thanks, Tom. And we're going to go 10 more minutes on Q&A. Understand if you got to hop off. We're going to go about an hour and 15 to an hour and a half on these webinars and try to get as many questions answered as we can. Remember, the links to future webinars and the January replay are in the chat. Also, if you want to download the handout for this webinar, click on the handouts tab, and it's in there's pretty big handouts, it's like over 10 megabytes. So go ahead and download that.
Strongly suggest to the audience, download that handout, because I think one of the gentlemen I saw pop into the chat was asking about the Megger insulation resistance. What are some good thresholds for go, no go? And in that section of the PowerPoint, you may remember there was a recommended minimum value of resistance table. So for, I think that question came from Joshua.
Joshua Johnson, LLR.
Yeah. Download the handout, Joshua, and the table will give you the minimum values that are recommended by the IEEE.
Awesome. So this is a great question that Joshua answered, because he phrased it when meggering a motor insulation. Like, meggering is like a verb now. That's awesome. Okay, so this is from Juan Montoya from Grupo Energia Bogota from Colombia. Thank you, Juan. What do you think is the best equipment to offline motor analyze? He said PDM. I guess he's talking about the PDMA, the MCE Max,
Yes.
or the Megger.
Yeah, there are a couple really good brands. The Megger, I think recently Megger reacquired Baker and the old AWA type test sets. So I think they are all under that Megger brand name right now. And then you have the PDMA, which makes both static offline testing equipment as well as dynamic online testing equipment. Both manufacturers, I really can't say a negative. Quality of product is very good. A lot of, in the static world, you'll find a lot of similarities between the PDMA and the Megger Baker product offerings. They'll do the insulation resistance, they'll do the winding resistance, they'll do the ramp test, they'll do the step voltage test. The big difference in the brands is the PDMA, unless they've changed something in their product portfolio, they do not offer the surge test, either the surge comparison or the pulse-to-pulse surge test. So that would be something very unique to the Megger, to the Baker AWA test sets that are out there on the marketplace. So I happen to really put a lot of faith in those tests. So that would be, I would lean a little bit toward those products that offer the surge testing, but that's just been my familiarity with the test over the years and, the answers that it has provided to me.
This is a great question too. This is from Fahad Sarwar. I hope I said that right. He's lead engineer at Fatima Fertilizer Company in Pakistan. The latest recommended life assessment tests, which should be part of routine predictive maintenance and annual maintenance.
That is again, that's a really, really nice. I like this whole focus into the predictive maintenance world. And as soon as I hear predictive maintenance, a lot of times my mind starts going toward online-based tests. So a couple of the things that I would probably say, again, going back to that partial discharge, you do have to take the motor or the generator out of service, and there are some capacitive couplers that would be permanently mounted and left into the equipment. But once that is done, you can do online partial discharge testing while the motor is in service, which is probably the best time to do the PD, because now you have the thermal, you have the mechanical aspects. So there may be PD events that are only stimulated and triggered by the thermal, as the mica flakes begin to separate, or through vibration, as like a loose bar starts rubbing and oscillating, and that's the stimuli to the PD. So that is a great test. You don't have to take the motor out of service, and you can trend this and look at how your insulation is deteriorating or aging. Is the problem out at the end windings? Is it in the core? Is it in at the conductor? So I put a lot of stock into that. Now there are others like vibration analysis, which we didn't even get into because it's more looking at the mechanical structure. But I'd say for predictive maintenance, things like the UV, partial discharge, and vibration analysis would be kind of my top picks.
Fantastic. Hey, let's circle back to Jonathan, because he actually had a question. It was a really good question as well. We got two more questions and then we'll wrap it up here. This question from Jonathan was, what is the biggest risk when working with this testing equipment for a technician?
Jonathan, that's a fantastic question, and I thank you for bringing that into these type of discussions, because sometimes we get our little propeller heads going and we talk about all the technical stuff and we forget about safety. But let's face it, we are dealing with test equipment that is putting out greater than 50 volts. Therefore, by definition, to NFPA 70E or to OSHA here in the United States, we are dealing with dangerous voltage levels, that can create dangerous shock levels. Okay. As I brought up in the webinar, when you are testing motors, you are testing large inductors. Coils are big inductors, and they store energy in the form of magnetic fields. So if you're doing winding resistance tests and you're pumping DC current into this winding, you are creating a huge magnetic field. Now, after the test, if you're using proper test equipment, most have discharge mechanisms built in order to help collapse that field safely and take down the stored energy. But if you're just going with like a standard low resistance ohm meter that's designed to like just test connection bonds or something, and it does not have a means to de-energize the winding, you could cause a huge inductive kickback, which could be lethal in some cases to the person. So you are dealing with test equipment that is putting out elevated voltages. So do your shock risk analysis, make sure that you wear appropriate PPE, make sure that the test equipment has discharging capabilities. So after the potentials or the currents are applied, any of the stored energy in the capacitance or the inductance of the specimen can be discharged safely. Again, Jonathan, thank you. Keep the eye on safety, brother.
Great. Thanks, Tom. And then the last question, and we'll wrap it up. From Matt Weintraub, is there any preference between AC and DC hypot tests for rotating machines?
Well, as you noticed, Matt, throughout the presentation, particularly when we're quoting from the various IEEEs, DC dominates in this field. The insulation resistance test is a DC test. The testing of high potential is all done at direct current. So when we really looked at almost all the static tests that we cover today and all of the references to IEEE, it's all been DC. And unlike cables, like if you attended last month, Matt, to the medium voltage cable, in the cable world, particularly with extruded dielectric cables, cross-linked polyethylene, or ethylene propylene rubber, the way this material ages over time and creates this phenomenon called water treeing, testing with direct high voltage direct current has been really kind of faded out of the industry because it actually causes accelerated growth of these fault channels. That is not the issue with motors and the tape insulators that are being used, the mica, the porcelain, the glass, and the, I'll just call more of a laminated type of insulating system. So DC is still very strong in testing of the rotating machines. Really, the only place where AC comes into place that I'm familiar with is when we do partial discharge testing. Power factor testing is done at AC, and SFRA is actually done with injected AC signals. But for most of the basic static tests, DC still rules.
Fantastic. So we have 2 minutes left. Tom, I think we have kind of one big announcement. Do you want to cover the 70E, the QEW course?
Oh, yes, thank you.
Dun, dun, dun,
dun. Hopefully, and Matt, you can slap me if I'm wrong on this timeline, but hopefully starting at the beginning of March, once we get back from power test, we are going to be introducing a electrical safety for qualified electrical workers training course. The course is going to be 2.5 days in length, and we will be covering all of the OSHA and NFPA 70E safety from a practical point of view. We're not just going to read you the book and allow you to draw the conclusions, but we're going to go through the 70E and OSHA requirements for electrical safety for qualified people, but we're going to put it in a practical sense from the perspective of, if you're on a job site, what does this mean? How does it affect your conduct? How does it affect the way you do things? And we are going to get deep into risk assessments, and we're going to be looking at recognizing of hazards. And we're going to go into areas like, what is capacitive coupling? What is magnetic coupling or electromagnetic coupling? What causes it? How can I make myself aware of it? So it should be a really fun course. I'm looking forward to it.
So look for more information on that through your email and through social media. That's going to be an exciting thing for us to launch here shortly. Thank you for your time. Thank you for staying up with us. If you're abroad, we will see you guys at NEDA Power Test, or we'll see you next month for Medium Voltage Cable Test and Diagnostics Part 2. Appreciate your time and have a safe day.